Hello guys, in the last class we had discussed about the basics of GOC. The first thing which we started was the carbocations, carbanions, radicals, what are intermediates, what are reaction intermediates, and what are different kind of reagents we basically deal with. So reagents as in electrophile, nucleophile, amphiphile. So these are few terms which we had learned in GOC, and now today we are going to start with electronic effects. So what are electronic effects? These are some temporary and some permanent effects which work on a molecule which is participating in the reaction. Because of these effects, the reaction takes place in a certain manner or it follows a certain course. So these effects work on an individual molecule which are the reasons for a reaction to happen in a certain direction or happen in a certain manner. Okay, so we will understand these electronic effects one by one. There are multiple which we are going to deal with. The first which we'll talk about is the inductive effect. As I mentioned, these effects can be temporary effects also, and these effects can be permanent effects also. Temporary means in the presence of some reagent, some effect came into the picture and will just the effect will get vanished as soon as that reagent will go away from the molecule. And permanent effect means where you can see the change throughout, as in like whatever that effect is, it is always there no matter the molecule is participating in the reaction or just lying idly. That effect would be working all the time. So this is what temporary and the permanent means. So let's start with the inductive effect. Okay, so first effect is inductive effect, the very basic one and the important one also. Now let's understand what is an inductive effect. So let's not go by the scientific terminology or the details of definition. Let's understand one thing. I hope you guys would have seen the tug war. Okay, so in tug war, there is one party which is winning and the one party which is losing. Winning means the one which is stronger party tends to pull the rest of the chain towards itself. Right, so exactly same thing happens in the molecules, especially in the organic molecules. You assume we have a chain of carbons, okay, and then there is a group attached somewhere. Okay, now depending upon the strength of that group, what do we mean by strength? Strength means electronegativity. Okay, so depending upon the electronegativity of the group, the shared pair of electrons or the electrons which are already there in the covalent bonding, they just shift or get tilted from one place to another. What exactly I mean to say? There were two species, A and B. Okay, just look at here on the board. Assume I have two species A and B. Now, as I mentioned earlier also, that suppose there is an electronegativity difference between A and B is capable of pulling the shared pair of electron towards itself. Then what will happen? There are two possibilities. Either the bond will break and B will swipe away the whole pair of electron and will get a negative charge, proper negative charge, and A will get a proper positive charge. But let's suppose the bond is not breaking. Okay, we are not doing anything to break the bond. It is just that B is more electronegative and A is less electronegative. So what we will do, the pair of electrons will always be under pressure to get attracted towards B. B will have general tendency of pulling the electron density towards itself. And because of that, it will gain a partial negative charge on itself. This partial negative charge is not because it has pulled both the electrons and then the bond is broken. It's only is, let's say you and me are sharing this pen, okay? And now suppose I'm more stronger, I'll pull this pen towards me. It is still in the shared mode, but it is a little closer to me. And when it is a little closer to me, this is like I am feeling more authority on this pen as compared to you, though it's just a pseudo feeling. But exactly the same thing is happening over here. When the electron pair is being shared between A and B, B is more electronegative and hence will pull the shared pair of electron towards itself, but will not pull it completely. Will just shift it towards itself and will have that feeling that okay, it is closer to me. And because the electron pair will be closer to B, B will gain a partial negative charge, not the proper negative charge. And because the shared pair has moved away from A a bit, that is why the A will have partial positive charge. Okay, so this is the concept of partial positive and partial negative. So this change is a permanent change in the molecule, because A and B are, when you talk about A and B are always different in electronegativity, no matter they are participating in the reaction or they are not participating in the reaction. So this effect will always be there. B will always try to pull the electron density towards itself, will always gain partial negative charge, and A will always be in the partial positive mode. So this is one general behavior of a compound when there are two elements of different electronegativity. Exactly same thing when it happens on the organic compound, we call it inductive effect. So exactly understand what is inductive effect. As I mentioned, I have, let's say, a chain of carbons. All the carbons are linked with each other through the covalent bond, and the carbon here is linked to a group over here. Okay, and again it is a covalent bond, and assume that G's electronegativity is greater than carbon's electronegativity. Then what will happen? This G will try to pull electron towards itself, irrespective of this compound right now is in the reaction or not in the reaction, or it's just simply lying anywhere. So G will always try to pull the electron towards itself, because of which it will gain a partial negative charge. And the carbon from where it is trying to pull the electron density, that carbon will gain a partial positive charge. And this effect, basically pulling of electron pair by G, or by the group which is present over there, or electronegative group which is present over there, is a kind of a rippling effect, of which is like transferring from one carbon to another. As I said, you assume it as a tug war. A very strong man is standing, and then there are like 4 or 5 people in a row who are holding each other, and the strong man pulls the whole chain towards itself. Then the pull will not be faced only by the first person, but the second person also, third person also, fourth person also. Obviously, the strength of pull will decrease when you will go as farther as, as you'll go farther, the strength of the pull will go down. The first one will face the strongest pull, second one will face a little lesser pull, and third one will face further lesser pull. So pull will be faced by the people who are standing in that queue, who are holding each other, and as the distance will increase, the intensity of that pull will decrease. So this G is, assume it's a very, very strong person standing in front and pulling the first carbon, or the electron density which is shared between carbon and this group. It will try to pull it towards itself, but in that pull, it's not only the first carbon which is coming into the picture, but other carbons are also getting included, just because they are all attached through a string which is bond. So it is not only first carbon which is getting affected, but the second one also, the third one also, though that pull faced by those carbons, the farther carbons, will be relatively lesser. It will keep decreasing as the distance will increase. So this exactly is your inductive effect. Okay, so what is inductive effect? As I mentioned, it arises due to the electronegativity difference, and this travel only within the single bonds. Okay, so there is a double bond, triple bond. These will not get affected by this inductive effect. Only sigma bonds are the ones on which this inductive effect operates. So this X is, assume, a halogen. Halogen has definitely better electronegativity than carbon. So this X will try to pull the electron density towards itself and will gain the delta negative charge. And this carbon, the first carbon which is directly attached to the halogen, will gain the partial positive charge. But as I mentioned, because other carbons are also attached through a string or through the bonds, they will also face that pull, and because of which the second carbon will also face a little partial positive charge, because they will also be pulled towards the X, or the electron density will be pulled towards the X. But the intensity of that positive charge is relatively lesser than the first carbon. Assume this is the carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. Intensity on the second carbon is lesser. On third carbon is further lesser. On fourth carbon is further lesser. So which is represented by delta delta plus, delta 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 plus, and so on. So to be very honest, on the after third carbon, the effect becomes almost negligible. So we don't even care what is fourth carbon facing, because there will be almost negligible effect, and you won't see any change in the reaction pattern because of any group present like 3 carbons before. Okay, so basically the inductive effect is visible only till 3 carbons. After that, it becomes negligible and we stop caring about it. Okay, so let's see the definition of inductive effect. This is a permanent partial displacement of sigma electron pair. As I mentioned, this effect works only on the single bonds, which we also call as sigma pair or sigma bond, and the electron pairs get pulled towards the more electronegative element, and this is called as inductive effect. Now that element can be carbon also, and that element can be other thing also, can be anything. Whichever is more stronger electronegative will pull the electron density towards itself from the other party and will gain the partial negative charge. Okay, so due to the electronegativity difference, what exactly happens? The poles get generated, you get partial positive, you get partial negative, and then partial positive positive or partial negative negative, depending upon carbon chain is gaining the negative charge or carbon chain is gaining the partial positive charge. Okay, what all different characteristics are there for inductive effect? As I mentioned, it arises due to the electronegativity difference operated only on the sigma electrons, and pi bonds do not interfere, so there will be no impact on the pi bonds at all. This you have to remember. Then, as I mentioned earlier also, that this is distance dependent, so farther carbons will not face the effect as prominently as the initial carbons would, and after 3 carbons the effect will become almost negligible. So this is a distance dependent effect and decreases drastically with the increase in its distance. Next, this effect is shown by arrows. Arrows means in which direction the electron density is getting pulled is shown by arrow. So if it is getting pulled this way, then it will be shown like this. So on the bond in between, you will put an arrow which will represent that the electron density is shifting from this place to this place, and the other way around. Okay, and this has an additive property. That means the vector sum, these are all vectors. This is direction dependent, distance dependent. So there, when you talk about the inductive effect, basically it works on the vector sum. It's not like a scalar quantity, it's a vector quantity. Okay, now when we talk about alkanes, all of the alkanes are non-polar molecules. They don't have electronegativity difference because this is carbon, 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 and so on. So if you'll talk about inductive effect shown by only alkanes, you cannot see that. Why? Because the carbons have same electronegativity. Due to the same electronegativity, no inductive effect works on alkanes. So they can ask you some tricky questions from this part, especially if they give you some compound like this, butane, pentane or anything, and they just draw their conformational isomers to confuse you. This is anti, this is gauche, this is your eclipse, partial eclipse, and so on. And they ask you what will be the in which the inductive effect will be more. So inductive effect will not be there in either case, because in every case your dipole moment is also gonna be 0. If dipole moment is gonna be 0, that means the electronegativity difference is not there. If electronegativity difference is not there, that means there will be no inductive effect which will be working over there. So inductive effect comes into the picture only and only when there is an electronegativity difference between the atoms which are connected through each other. Okay, we don't talk about carbon and hydrogen over here. We talk about carbon and some other species, other group which is present there. So if there is an electronegativity difference between these atoms, then only the inductive effect will work. Otherwise, in normal alkanes, it will not. Now, why I'm repeatedly mentioning only alkanes, not alkenes and alkynes? Because in alkenes and alkynes, the hybridization changes. That means in alkanes, all the carbons will be sp3 hybridized, whereas when you talk about alkenes, there will be some set of carbons which will be sp3 hybridized, there will be some set of carbons which will be sp2 hybridized or sp hybridized, depending upon it is an alkane or it is an alkene. Now, with the hybridization change, electronegativity changes. For example, if I compare sp3 hybridization, the carbon which has sp3 hybridization, carbon which has sp2 hybridization, and carbon which has sp hybridization, all the three are carbon only, but the hybridization is different. So sp hybridized carbon is gonna be more electronegative than your sp2 hybridized carbon and then sp3 hybridized carbon. Okay, so even if the atom is same and hybridization is changing, electronegativity will change. That is why I didn't mention alkenes and alkynes over here. I just mentioned alkanes. Alkanes have no electronegativity difference, hence no inductive effect, but inductive effect will work in case of alkenes and alkynes. Okay, we'll come to this hybridization part once more when I'll tell you in detail that what all different type of inductive effects are there and how do they work and what all different groups comes under that. So that we'll be comparing again. So in the next slide, we'll be talking about the types of inductive effects. So now we have understood what is inductive effect, and now we'll understand what are different type of inductive effects can work on a carbon chain. So basically inductive effect works on only one single funda, that is difference in electronegativity. So now there are two possibilities. One is the group which is attached to the carbon chain is more electronegative and hence pulling the electron density towards itself, or it can be other way around where the carbon is more electronegative or the chain is more electronegative and pulling the electron density towards itself. Okay, so there are two possible cases and hence there are two type of inductive effects. Now first type of effect is plus I effect. Okay, so what is positive inductive effect? Positive inductive effect is when the group is electron releasing. That means the group to which we are referring is electron releasing group and rest of the chain is getting the electron density and group is giving the electron density. So that means the carbon chain or any chain will have the delta negative charges on them and group will have delta positive. So basically whatever group is present, that is electron donating group. So it will give away its electron density and gain partial positive charge, whereas the other part of the chain, there are two parts of the chain and one part is the group and other part is the chain. Chain is gaining negative density and the group is gaining positive charge. Okay, so this happens when there is an electron releasing group present. Okay, so this situation will appear only and only if there are electron releasing groups present, and these electron donating groups will give away the electron density and will gain the partial positive charge, whereas the carbon chain which is attached to it will gain delta negative charge. Again, the first carbon will have delta negative, second carbon will have delta negative, and so on. So here these carbons can be the normal carbon chain or it can be carbon based functional groups also. It can be either way. For example, if I write it this way, let's say if I write COH and CH3, just assume I have written it this way. So basically CH3 is electron donating and COH is electron gaining, right? So if the bond is between this carbon and this carbon will gain positive charge and this carbon will gain negative charge. So it need not to be necessarily the carbon chain. It can be any carbon based group over here or anything. Okay, and this group can also be anything. So that means when in the chain one is electron releasing group present and the other part is gaining the negative density, then the effect is called as plus I effect. Okay, plus I effect, what will happen to the plus I effect? As we'll go farther in the chain or as the distance will increase from the electron donating group, the effect of electron donation will decrease and the negative density will decrease on the carbon chain. Okay, as I have shown over here, first carbon is delta negative, next is delta negative, then delta negative. So when we are going towards the farther end, the electron density is decreasing or the effect of electron donation is decreasing. So what all different groups are there which can act as electron donating group? There are the alkyl groups itself which will act as an electron donating group. So anything which is attached to the alkyl groups will act as the electron acceptor, or you can say the electron density will increase in that area, and carbon chains or alkyl groups will lose the electron density or basically will donate the electron density. So there is no complete donation, but at least will shift their electron density towards the rest of the chain. Okay, so electron releasing groups are nothing else but alkyl groups. So we can have different type of alkyls. We can have methyl, we can have primary alkyl, we can have secondary alkyl, we can have tertiary alkyl. So if you talk about the stability or if you talk about the donation capability, more the degree of your carbon is or more the number of carbons are there in the alkyl group, more will be the donation capability. So if degree is higher, degree of carbon is higher, then donation capability is more. Donation capability is more. Okay, and this is one thing. And if the number of carbons are more, number of carbons in alkyl group are more, then donation capability will be more. So basically if the number of carbons are increasing, donation capability will increase. Donation capability is more. I have just written increases over here. Number of carbons are increasing in the alkyl group, the donation capability will increase. So basically degree of carbon changes the donation capability. That means more higher the degree of the carbon is, more donating that alkyl group would be, or the more number of carbons present in the chain, more donation capability that particular alkyl group would be having. Why, how, we'll see next. So basically, each carbon has a donating capability. Now let's try to understand it over here. How higher degree is more donating? Just look at this molecule. Now this carbon is attached to something, let's say, is attached to A, assume, and A is electron withdrawing and carbon is electron donating. This carbon is getting electron density from CH3, from CH3 and from CH3. So CH3, CH3, CH3 are giving to the center carbon, and center carbon is pushing that electron density towards A. Right? So 3 carbons directly giving electron density to carbon, and that carbon is pushing it towards A. So basically, directly 3 carbons are donating to one center carbon, and one center carbon is pushing the electron density towards A. Whereas if you look at this, again, this molecule has the 4 carbons, okay? But here the distance is increasing. So this carbon is giving directly electron density to this carbon. This carbon is also giving direct electron density to the CH, but CH3 is a little farther, so donation capability will decrease, right? As the distance will increase, the donation capability will decrease. So direct attachments with the center carbon is just 2 CH3s or 2 carbons, okay? And the CH3, which is just behind it, is little farther, and hence the donation capability will be lesser. So 3 direct attachments will have more electron donation because each carbon has its own donation capability. So 3 direct attachments will give more electron density. 1 indirect attachment, or you can say 2 direct attachments and 1 farther attachment, the donation capability will decrease. And if the chain is further longer, so if I have again 4 carbons but not as branches but connected one behind another, this is direct donation, then this is little farther donation, then this is farther donation. So what will happen? Only 1 carbon is directly giving its electron density to the first carbon which is present over here. Other 2 are a little farther, hence the donation capability is lesser. So distance, if it will increase from the center carbon which we are referring to, which is giving the total electron density, which is acting as an electron releasing center for some other group or some other molecule or some other chain part, let's say A. So center carbon is acting as an electron releasing group for A. Now, how much electron density it is receiving from rest of the carbons, that will depend whether the carbons are directly connected to the center carbon or they are connected in a length. Basically, with the distance, the things are changing. Okay, with the distance, the carbons are becoming farther, or they are present in the farther situation, and hence the electron density donation capability will decrease. Okay, that's the reason why if the degree is higher for the carbon, that means more and more carbons are directly attached to the center carbon which we are referring to, then the electron donation capability will be more. So you can say tertiary will have more electron donation capability than secondary, then primary, and then methyl. Okay, so carbon chains or alkyl groups are always electron donating unless they are attached to a metal. Only from metals they can actually get the electron density. But if you're talking about any other thing, any other group, they will be always electron releasing. So they will be acting as electron releasing groups, and other part will be acting as an electron withdrawing group. Okay, so whenever you talk about the chain where there is an electronegativity difference, there is always this thing that one part will be electron releasing and another part will be electron withdrawing. So that means unless a metal is present along with the carbons will always act as electron releasing groups, and other group will always act as an electron withdrawing group. If the metal is present along with the carbon, then only carbons will pull electron density from there. So you can see an example over here. I have a chain over here and MgX. So carbon is connected directly to magnesium. So here magnesium is metal which can donate electron density to carbon or can push the electron density towards the carbon. So carbon will gain a negative charge over here and Mg will gain a positive charge here. Otherwise, in all other cases, carbon chain will always have partial positive charge and the other group will always have a partial Negative charge, because all the groups which we treat as functional groups, or the groups which are made up of oxygen, chlorine, bromine, nitrogen, all these groups have the elements which are better electronegative than carbon, and hence they will pull the electron density from the chain. Okay, so this means whenever at any place the carbon is present, that will always act as electron releasing group and will always gain a positive charge on itself when we are referring to that carbon as a group. Okay, in that case we will say that this particular carbon is showing its plus I effect. For example, let's say if I have a benzene chain, okay, and I have a CH3 present over here. Now if somebody refers to this CH3 as a group, okay, and asks what kind of effect this CH3 will show on benzene, so this CH3 is always electron donating and will show plus I effect. It will always push its electron density towards the rest of the carbons of benzene. So I told you, if you have an sp2 hybridized carbon and you compare it with an sp3 hybridized carbon, the electronegativity of sp2 hybridized carbon will be more, whereas sp3 will be less, right? So here in the benzene, all the carbons which are present are sp2 hybridized, hence higher in electronegativity. So electronegativity difference is there. And at that time, if you refer CH3 as a group, it is donating group, and benzene will act as electron withdrawing area. So the carbons which are present on this benzene will be accepting the electron density. So basically will be carrying delta negative charge, whereas CH3 will be carrying delta positive charge. Okay, we will deal with it in much more detail, and you'll get to know where this plus I effect we can use and how we can say ki alkyl groups are acting as a plus I group and what will be their impact on the overall system. We will see this in many of the examples. So wait for the examples so that you can understand what is the usage of this plus I effect. Minus I, all of us would have understood, and it is pretty clear also that any electronegative element will pull the electron density towards itself. So minus I, understanding minus I is not as confusing as understanding plus I is. Okay, now apart from that, what else can act as a plus I group? One is alkyl group, we have got it. Apart from that, is there any other group which can act as a plus I group? Yes. So if we have any element which is carrying a negative charge on itself, or if we have a group which is carrying a negative charge on itself, irrespective of its electronegativity, it can be very highly electronegative, or it can be average electronegative, or it so basically even if its electronegativity is more than carbon, but still if it is carrying a negative charge, then it will act as electron donating group. Why? Let's understand. Assume I have oxygen which has a negative charge on itself. Okay, oxygen's general nature is to withdraw the electrons, or it is higher in the electronegativity. So wherever it will be, or let's say it is bonded with a carbon in some sort. So let's say if the structure is like this. Okay, so in this case what will happen? This oxygen is electron withdrawing. Why it is electron withdrawing, or why it is higher electronegativity? We have already learned this in periodic table, that the electronegativity of oxygen is higher than carbon. So when it comes to create a polarity in the bond between carbon and oxygen will pull the electron density, will gain the negative charge, and carbon will gain the positive charge, right? But instead of OH, if I write CO minus, assume, okay, in this case what can I see is my oxygen is already carrying a negative charge, right? And if you look at the electronegativity, if assume you talk about electronegativity difference, and let's do it with respect to electronegativity difference. If we feel that oxygen will pull the electron density, there is already the negative charge, and the shared pair of electrons will come closer to the oxygen. So what would we expect? We expect the repulsion over there. First of all, excess of electron on oxygen, plus the shared pair of electrons are also shifting towards oxygen. So what will happen? The repulsion between the negatively charged oxygen and those bond pair electrons will happen. Okay, so rather than trying to accept that electron, it will push away from itself. So it will try to avoid the repulsion as much as possible. Even though oxygen is electronegative, still it won't be able to pull the electron density towards itself, because it will face high repulsion. Instead, it will try to make a distance from the electron density due to its negative charge. And if it will try to maintain some distance, it will push the shared pair of electron towards carbon, and automatically the carbon will be delta negative. So basically electron density will be pushed towards the carbon chain, and so O minus will act as electron donating group over here. Just because excess of electron density which will come or which will surround the oxygen will have repulsions, and to minimize the repulsion, oxygen will push away the electron density towards the carbon, and that is the reason why it will act as plus I group. Okay, so any electronegative element or any group, if it is carrying a negative charge, it will not be able to accept more electron density around itself, even though its electronegativity is high, and hence it will push away the electron density towards the carbon chain and will act as plus I group. It's not only about O minus, it can be any group carrying a negative charge. Okay, so irrespective of the electronegativity, if there is a negative charge on the group, it will automatically act as plus I group and will push away the electron density towards the carbon chain. It will push it away from itself, and the carbon chain will, or the carbons which are attached to that particular group, will carry a delta negative charge. Now let's understand what is minus I effect. Minus I effect we have already understood actually. So this is just a quick brief. What is minus I effect? It arises due to the electron attracting groups or electron withdrawing groups. So basically, if any group which is present on the carbon chain is more in electronegativity than carbon, then it will pull the electron density towards itself. It will pull the shared pair of electron between carbon and that group towards itself. It will not break the bond, but at least it will pull it towards itself a bit, because of which it will carry negative charge and the carbon attached to it, and rest of the carbons will get the partial positive charge. So this effect, when the group which we are referring to is getting a delta negative charge, is called as minus I effect. So here just see with this we have already seen earlier. So I think there must be one more carbon over here. I have missed it by mistake. So this is my chain, this is the group, this is more electronegative, group is more electronegative than carbon, and hence it is carrying the delta negative charge, and all the carbon chains are pushing their electron density towards G. We already have learned this, the alkyl groups are in general, or the carbon groups in general, are electron donating. So they will donate their electron density towards that functional group, and that functional group will pull the electron density. So automatically the group will carry negative charge. Carbon will get partial positive, and the farther carbons will get the positive charge, but the density of positive charge will decrease and it will become negligible after third. So on fourth carbon, what is the positive density? We don't even care about it. Or what is the partial positive charge? We don't even care about it, because it is negligible and will have no impact on the reaction mechanism. The same way how plus I decreases with the distance, same way minus I will also decrease. In fact, any kind of inductive effect will decrease with the distance. So this is distance dependent. More farther carbon you will refer to, lesser will be the impact on it, no matter you talk about the plus I effect or you talk about minus I effect. What all different kind of groups can be electron withdrawing? All the groups which carry electronegative atoms will act as electron withdrawing groups. So their electronegativity must be higher than carbon. That's all is the requirement, and all these groups will act as electron withdrawing group and will carry negative charge when will be attached to the carbon chain. For example, you have C triple bond N, COOH, COOR, OH, OR, X. All these groups, if you see, have electronegative elements present in it. Or the carbon, like let's say if you talk about CN, in this case C is sp and nitrogen is also sp hybridized. So basically either the hybridization should be different, or the electronegative element should be present in the group that will create the poles, and that will create the electronegativity difference. Anything which is higher in electronegativity will act as electron withdrawing group and will show minus I effect. Okay, so let's see some examples of minus I effect. Let's say if I talk about the first example, what can I see is on the carbon chain there is one fluorine attached to it, then on the carbon there are two fluorines attached to it, and on the third carbon there are three fluorines attached to it. So basically the functional group which we are referring to here right now is fluorine. And if only one fluorine, if you talk about the fluorine carbon bond, fluorine is more electronegative than carbon and definitely will pull the electron density towards itself, right? So this F is electron withdrawing group and carbon will act as electron donating group. So if I am referring to fluorine, fluorine is an electron withdrawing group and hence will show minus I effect. Okay, but just understand this thing. I have carbon on which I have attached a group over here. If I have one group present which shows minus I, or if I have two groups present which show minus I, in which case it will experience the more inductive effect when more number of groups are present on that carbon. If there are more number of electronegative atoms present in the group, or multiple electronegative groups are present on the carbon, then carbon will experience the higher inductive effect. So with the increase in the number of the functional group, the inductive effect also increases. So, or electron withdrawing capability increases. So here is only one fluorine. It will withdraw electron density till a certain extent. We have two fluorines over here. The withdrawal of electron density will be more in the second case, and it will be highest in case of third. 3 electron withdrawing groups are present, so they'll be able to withdraw a lot of electron density. So inductive effect faced by the carbon on which 3 fluorines are present will be maximum. So if somebody asks where is the minus I effect maximum, it is maximum in the third case. Okay. Similarly, if you remember, I mentioned that if the percentage S character increases, that means if the hybridization changes, then electronegativity of the atom also changes, no matter we are talking about the same element. So I told you, if you are talking about sp3 hybridized carbon, it is less electronegative than sp2 hybridized carbon, and then further this is less electronegative than sp hybridized carbon. So basically, if you look at this, percentage S character is increasing when we are going from sp3 to sp. So more percentage S character is, more will be the electronegativity of that atom. Okay, so I have taken the example over here. More the electronegativity of that atom, more will be the electron withdrawing capability, and more will be the capability of showing minus I effect. If it is more electronegative, it will pull electron density with a strong force, and hence the inductive effect shown by that particular group will be more. So look at this example. I have taken an example over here. I have written CH3, CH2, NH2. So nitrogen is the group over here. If you look at the nitrogen's valence, nitrogen's hybridization, it is sp3 right now. Then let's say if I talk about imine is another group. CH double bond NH is an imine group. So if I'm talking about this group here, the nitrogen's hybridization is sp2, and then if I come to C triple bond N, in this case the nitrogen's hybridization is sp. So which nitrogen will be capable of withdrawing more electron density? The one which has more percentage S character. So basically the nitrogen of the C triple bond N is strongest electronegative among all the other nitrogens. So nitrogen which is sp3 and nitrogen which is sp2 are lesser electronegative than the nitrogen which is sp. This is something which is very important, and you should know this. Next, if I have to compare the electronegativity of carbon and nitrogen, or if I have to talk about, let's say if there is a case where we have carbon and we have nitrogen, and they are following specific hybridizations, how to decide which one will act as an electron withdrawing and which one will act as an electron releasing part. In general, when you talk about the electronegativity of carbon and nitrogen, carbon is lesser electronegative than nitrogen. Okay, so if I have to compare between sp3 nitrogen and sp3 carbon, in general, nitrogen is more electronegative than carbon. Here the hybridization is same, percentage S character is same, so the behavior will also remain same. So that means here also nitrogen will be more electronegative than carbon. Okay. Similarly, if you compare between sp2 hybridized nitrogen and sp2 hybridized carbon, again nitrogen will be more electronegative. Come to the third case. If I have sp hybridized nitrogen and sp hybridized carbon, which will be more electronegative? Sp hybridized nitrogen. But where is the exception? Exception is when you are comparing an sp3 hybridized nitrogen and sp hybridized carbon. In this case, your carbon will be more electronegative than nitrogen, and it will pull the electron density, whereas nitrogen will give the electron density. Let me just show you an example. Let's say if I write the structure like this, if I write it like this, and if I ask you to show the direction from where to where electron density would be moving. So here if you talk about nitrogen, this is sp3, whereas if you talk about this carbon, this is sp. So your carbon is more electronegative than nitrogen. So here your nitrogen will have a partial positive charge, whereas this carbon will have a partial negative charge. So such kind of cases are a little tricky, where you have to see whether carbon is more stronger electronegative or the other element is. That will be completely on the basis of the hybridization, and this is the only exception. Basically, you can say sp3 hybridized nitrogen is lesser electronegative than sp carbon. We are nowhere relating it to sp2 carbon or anything, and you won't find such comparisons also. Okay, you won't get such questions where sp3 hybridized nitrogen would be compared by sp2 hybridized carbon. We don't do it, okay, because all these are experimental values and you can calculate them, and we are not calculating it right now, so you cannot just do anything on the basis of assumption. So this is the known fact, and this is the exception, that sp3 nitrogen is lesser electronegative than sp carbon. But if it would be a case of sp3 nitrogen with sp2 carbon, then the data will still remain the same. sp3 hybridized nitrogen will be a better electronegative element than sp2 carbon because of its positioning on the periodic table. Okay, so this is the only exception, and this is an important exception. Now we have understood that the electronegative elements acts as a minus I group. We also have understood that higher the hybridization is, or higher the percentage S character is, more stronger electronegative the element would be and would show better minus I effect. Apart from that, do we have any other groups which can show minus I effect? So yes, if the group has positive charge, if any group has a positive charge irrespective of its electronegativity, then what will happen? The electronegativity will increase. So what is electronegativity? Electronegativity is hunger for the electron. If anything is already carrying a positive charge, that means it is deficient of electron, and it would desperately want to look out for the electron density. So if any positively charged species is attached to the carbon, then it will act as a very strong electronegative element, and hence will pull the electron density from that shared pair very strongly. Pull as in it will shift the electron density very strongly towards itself and will nullify its positive charge. So it won't carry a negative charge, but it will nullify its positive charge. So basically its positive charge will get subside, or it will decrease when it will pull the electron density. Why? Because positive elements, or the elements or the groups which have positive charge, are anyways very hungry for electron. Now when they are attached to a shared pair of electron, or they are forming a bond, they will desperately try to pull that electron density towards themselves to satisfy their hunger and decrease the intensity of the positive charge. Okay, for example, if I have the comparison between CCOH, CCO minus and CCO plus, if somebody asks me in which case my oxygen will show the highest electronegativity, though the element is same, where the minus I effect will be maximum prominent, it will be maximum prominent over here. Why? Because oxygen is anyways an electronegative element, and now it is carrying a positive charge. That means whatever the normal hunger it had for electron, it has got increased drastically. It has got increased due to the positive charge, and it will pull the electron density towards itself very strongly, or it will pull the shared pair of electron towards itself very, very strongly to decrease the intensity of the plus charge it is carrying. Because element, no matter it is carrying a plus charge or it is carrying a negative charge, if there is a charge or anything, then that particular species is not very stable. Charges do not make any element stable, it makes them unstable. Okay, so anything which is carrying a positive charge or a negative charge is anyways in an unstable mode, and it would like to become neutral as early as possible, either by making bond, or by losing electron, or by gaining electron, or whatsoever is possible. Okay, so here this will show the maximum minus I, this will show normal minus I, and this will actually show plus I. Why? Because it will not be able to pull electron density towards itself due to the repulsion. Instead, it will push away the electron density, and hence there will be a delta negative charge here, and it will carry a delta positive, which will basically nullify this negative charge. So neither there will be negative charge nor there will be a positive charge. Basically negative charge will be there, but the intensity of negative charge would have been gone down drastically. Okay, so in this case your oxygen will act as a plus I, in this case it will act as a minus I, here also it will act as a minus I. So let's mark it as minus I3 and minus I1, but minus I3 is much greater than minus I1. Okay, so that means electronegativity of a group increases if it is carrying a positive charge, because hunger towards the electron increases and it becomes more stronger electron withdrawing. So if I say that compare the electronegativity of O plus, N plus, O and N. First of all, in general, in the periodic table, oxygen is more electronegative than nitrogen. So if I am comparing O plus and N plus, O plus will be more electronegative than N plus. Okay, and then if the comparison is between oxygen and nitrogen, N plus, that means N carrying a positive charge will be stronger electronegative than normal oxygen, because hunger for electron is more because it is carrying a positive charge. So the order would be O plus will be more electronegative and hence more electron withdrawing, then N plus, then oxygen, and then comes the nitrogen. So here you cannot say because oxygen is placed at a better position or the later position with respect to nitrogen, and hence N plus should have lesser electronegativity than O. Here it is N plus, it is not N. N plus has a positive charge and it will act as a very strong electron withdrawing group due to the positive charge which it is carrying, which is increasing the hunger for electron. Okay, so this thing you have to understand. Now let's see. Similarly, I have taken a case where I have taken NF3, NH3 and NO2. NF3, and it is carrying positive charge. Nitrogen is anyways electron withdrawing group, right? And then it has a plus charge on it, and along with the nitrogen there are further 3 fluorines attached which are also electron withdrawing. Okay, so basically this nitrogen is carrying positive charge and carrying 3 electron withdrawing groups with it. So these fluorines are pulling electron density towards themselves when we are referring to the bond between nitrogen and fluorine. They are not donating electron density, they are pulling the electron density from nitrogen. So nitrogen is anyways carrying positive charge, then it is attached to further electron withdrawing group. So this positive charge intensity has been drastically increased due to the presence of fluorine. It is like I'm already poor and then somebody is snatching that a little bit money what I have from my hand, that also it is getting snatched, so I'll become more poor, or I'll be poorer than before. So that's exactly is what happening to this nitrogen. It already was carrying a positive charge, then it is attached to fluorine which is furthermore electronegative, and it will pull the electron density strongly towards itself from the nitrogen. So the plus charge intensity is actually more than what it looks like. Okay, and hence the hunger for electrons will be also much stronger than what it looks like. It's just not plus positive, it has the effect of fluorine also. Whereas when you compare it with NH3, in this case what is happening, nitrogen is carrying a positive charge, nitrogen is more electronegative than hydrogen, so it will pull small electron density from hydrogens, and hence the plus charge which looks like 1 unit is not actually 1 unit, it is relatively lesser than that. So but it has N positive. That means even if the slight positive charge is there on this nitrogen, it will have a better hunger for electron than a neutral nitrogen. Now come to NO2. Now in this case of NO2, nitrogen doesn't carry any positive charge, so hunger for electron would be relatively lesser than N plus, no matter in whatever case. So if I ask you which of these groups will show maximum minus I, NF3, extremely hungry. Then NH3 plus, it is also pretty much hungry because nitrogen is carrying a positive charge. NO2 is lesser hungry than the NF3 plus and NH3 plus because it is not carrying a positive charge and it will behave normal, how a normal nitrogen behaves. Whatever the electronegativity of nitrogen is, it will behave in that manner, and accordingly it will implement its effect on the carbon chain. Okay, so this is about comparing between the groups when it comes to you, that which one will act as more electronegative element and which will act as less electronegative element, or which will act as a more electron withdrawing group and which will act as a less withdrawing group, and accordingly you can mark where the inductive effect is more visible or minus I effect is more visible, where it is less visible. So such kind of questions they ask you. Okay. Apart from that, one more thing you have to understand. I have spoken about the oxygen, nitrogen and all these elements can carry a positive charge. So isn't it against their policy or against the electronegativity? I mean, they should not lose electron, they should always gain electron. So basically in an ideal situation, they should not carry a positive charge. Okay, so if they're carrying a positive charge, they're anyways very unstable. The only time when they can carry, I mean, even carrying that positive charge itself, very less possibility. Where in which all cases oxygen, nitrogen and similar electronegative elements can carry a positive charge? Only in those cases where the octet rule is not getting violated. Let me show you example. If I have the case like, it is connected to some chain, and then I have O plus and this, and this. So look at this species. Look at the species right now. So carbon's valencies are fulfilled. Look at the oxygen's valency. 2 electrons here, 2 electrons here, and 2 electrons here. So basically 6 electrons it has. 2 in the bond pairs and 4 in the lone pair form. So overall electrons which are there in this O plus are 6 electrons, which is defeating the octet rule. If any such condition comes, if the configuration of element, or you can say it is violating octet rule, then that species is not possible. Then that species is just an imaginary species, because it is highly unstable and it will not form such compound. But if I have the condition like this, CH2O. Now let's say if this is the case where oxygen has completed its octet, I mean the octet of the oxygen is already complete and still it is carrying a positive charge, then only and only in this case your oxygen or nitrogen or any electronegative element can carry a positive charge. So its octet must not get disturbed. Its octet must not get disturbed if it is carrying a positive charge. If it is not following the octet rule, then the stability of that positively charged electronegative element stability is very less, and hence it will not exist. Okay, so look at this example which I have shown you over here. I'll tell you in which cases the octet is not violating and still the electronegative element is carrying a positive charge. We all know the bonding of H2O. So H2O is like this. Okay, now from somewhere, let's suppose H plus comes, and this H plus is a positive charge. This will get attracted towards this pair of electron, and eventually what will happen, this you would have learnt in grade 10th. This H2O will this oxygen will give its lone pair to hydrogen to make a bond, and this will become this. The donation of electron pair will happen. Hydrogen will form the bond with oxygen, but oxygen will get a positive charge on it. Why this oxygen will get a positive charge? Because it has given one of its electron to hydrogen. Hydrogen didn't have any electron, it was H plus. So one electron it kept with itself, one electron it has given to hydrogen, so that both can share those electrons and can form a bond. Hydrogen gained one electron from oxygen to form a bond. So earlier oxygen has 4 free electrons lying just like that. Now it has 2 free electrons or two lone electrons present over there, or one lone pair present there, and another pair of electron which was just sitting idly earlier is now participating in the bonding. One electron is with oxygen and another electron oxygen has given to H plus, so that H plus can have one electron to form a bond. So donation of that electron has happened on hydrogen, and that's why it is carrying a +1 charge. But if you look at overall number of electrons, is it changing? See, 2 bond pair of electrons, 2 another bond pair of electrons. Then here this bond is also made up of 2 electrons. So 2, 2, 2, 6 and 1 lone pair. So 8 electrons are still maintained, and still your oxygen is carrying a positive charge. This kind of species is possible. So your electronegative elements can carry positive charge only and only if their octet rule is not violated. If the octet rule is violated, then those species are not possible, and those are highly unstable species. So we will say that the question is wrong. I mean, here the atom's octet rule is not getting followed, and hence this O plus is nowhere acting as a minus I group. It is just a wrong question altogether. Okay. So positive charge at oxygen, nitrogen, or any electronegative atom with the incomplete octet makes the group highly unstable, and hence such groups do not exist. Okay, so I hope you have got clarity what is plus I, what is minus I, and what kind of groups can exhibit these kind of effects. Now let's understand what is the application of these concepts. What we have learned what is minus I effect, we have learned what is plus I effect, how and where all we can use this inductive effect in solving the questions. So one more small thing before we move to the applications of inductive effect, and that is if we are talking about the plus I effect. Okay, even hydrogen tends to show the plus I effect because hydrogen is the least electronegative element, or you can say most electropositive element. And when it is attached to carbon, it will be giving some electron density to the carbon. electron density will be pulled by carbon and hydrogen will be giving away the electron density. So here comes a comparison. When you're talking about, let's say, the isotope of hydrogen and hydrogen, so basically deuterium and hydrogen, these are two basic isotopes of hydrogen which we deal with. Tritium we don't deal with much. So if I have to compare the D's plus I effect and hydrogen's plus I effect, or H plus I effect, then in that case D tends to show a better plus I effect, basically better electron donating effect than hydrogen. Why is it so? Because when you talk about the atoms, they basically vibrate when they are in the bonded form. Okay, so when you talk about deuterium, it's little heavier and hence it vibrates relatively lesser. When it vibrates relatively lesser, so the overlap which happens in the orbitals to make the bond, that overlap is much more effective in case of deuterium because it is not vibrating or shaking as faster as hydrogen. So that overlap is very effective between the orbitals and hence the bond is relatively stronger. Okay, it is relatively stronger, it is more stable in the terms of, because the overlap is better, it can donate much effectively rather than the hydrogen is shaking, the overlap is not very efficient, and hence the donation capability is also not very good. So even if you don't remember the reason why, you can just remember that deuterium is it gives better electron density or is much more efficient in donating the electron density or pushing the electron density towards the carbon or any other electronegative element per se as compared to hydrogen. Okay, so let's say if somebody asks me if I have CD3 and if I have CH3, these are the two groups. Overall, I had mentioned that carbon is also electron donating with respect to any other element or with respect to any other group. So as a whole, CH3 group will be electron donating group. Carbon will be getting electron density from hydrogen and carbon itself will be giving electron density to the rest of the part of the chain. Okay, so this, if I ask which will tend to show better electron donating capability, CH3 or CD3, it will be CD3. Why? Because carbon is getting better density, better electron density from deuterium, and hence it has more electron density to push towards the rest of the chain or rest of the group or whatever we are referring to. So let's say if I talk about, this is my benzene, I'll take the same example. I have CD3 attached and I have a CH3 attached. So which one will tend to show better plus I effect or better electron donating effect? CD3 will tend to show better electron donating effect because D is better donating here and hydrogen is lesser donating here. So the donating capability of deuterium to the carbon is more and hence the overall density will be donated better by this carbon to the benzene chain or benzene's carbon. Okay, donating as in we are not completely donating but pushing the electron density, but that push of the electron density is also more and effective in case of CD3 as compared to CH3. So this is also very important part. They give you some questions like this where they have compared it with deuterium and all that. So you should know how it creates difference when there is a deuterium instead of hydrogen. So let's begin with the application of inductive effect, and the first application is understanding the stability of carbocations, carbanions and carbon radicals. So if you remember when we started this topic, I had explained you what exactly are the carbocations, carbanions and carbon radicals, and at that time I had written an order of stability, and I told you that we will come to the stability order later on with the reasons that why this is the stability order, why we say for a carbocation, tertiary carbocation is more stable than secondary, then primary, then methyl, or benzylic and vinylic carbocations are more stable than your other carbocations. So all those stability orders we had discussed, but we had just spoken about it like a fact and we didn't speak about the reasons behind it. Now with the help of inductive effect, it will be easier for us to understand a part of stability order of your carbocation. Okay, so first of all, we'll understand again what is carbocation and then we'll talk about the stability order. What is carbocation? Carbocation is the species which is an intermediate species which is in which the carbon is carrying a positive charge. If you look at the hybridization of the carbon, here the carbon will have a vacant p orbital. Okay, the carbon will be having a vacant p orbital, you can see it over here, and the rest of the three hydrogens, or it can be hydrogen or it can be other R groups, anything it can be. So on three attachments or in three bonds, the groups will be attached and carbon will be carrying a positive charge, and that positive charge is basically the empty or vacant p orbital. So we can say this is the reaction intermediate. We have already spoken about it. My carbocation is nothing else but a reaction intermediate. It is short-lived. Why it is short-lived? Because it is unstable species. Any species which has a positive charge or a negative charge is an unstable species, and they would like to become neutral. And because they would like to become neutral, they are short-lived. Okay, and that is why they are called as intermediate. You would never see any product being charged or product having any charges on it. Anything which is charged is always intermediate, and it will always move towards the neutral structure. It will always try to become neutral, and once it will become neutral, that will be your stable product. Okay, so this is short-lived, highly unstable. Now look at the species very carefully. If you talk about the lone pairs, if let's say I speak about this carbocation, this is, let's say, the carbocation. This is the simplest carbocation I have taken. So here, can we see any lone pair present on the carbon? There is no lone pair on the carbon. How many bond pairs are there? There are 3 bond pairs are there. So basically 6 electrons are there. Number of unpaired electrons are there. Any unpaired electrons? No unpaired electrons. So 0 unpaired electrons. And what kind of hybridization does it follow? Generally, carbon with all the 4 single bonds follow sp3, but as soon as it loses a hydrogen or any other attachment, so basically if its one bond becomes free and it gets a positive charge, then the hybridization shifts from sp3 to sp2. So that means the 3 attachments or the 3 groups which are present on the carbon are attached to the sp2 hybridized orbitals, and one p becomes an unhybridized orbital. Okay, so you can see this vacant p unhybridized orbital over here. So the hybridization is sp2, and hence the shape is trigonal planar. Now total number of electrons which are present on a carbocation are 6 electrons, because it has lost its own electron plus 1 shared electron. So it has 6 electrons with it. 6 electrons in any species means it is electron deficient, and if any species is electron deficient, then what it can be called as, it can also be called as electrophile. So we can call it as electron deficient species. We can also call it as electrophile. Okay, so this is about some basic information. This is some basic information about carbocations, and now let's see how inductive effect changes the stability of a carbocation. So just understand one thing. As I mentioned earlier, and I'm again and again repeating the same thing, if anything is charged, then it is unstable. So it will try to get rid of that charge. Now, if I have a carbon carrying a positive charge, that means it wants to get rid of this charge. How can it get rid of this charge? By gaining electron density from somewhere. Or if I attach something on this carbon which can donate some electron density to this C+, then what will happen? The intensity of this plus charge will decrease. Decrease in the intensity of the plus charge will make this carbocation more stable. So if any electron donating group, any group which can donate electron, any electron donating group, if it will be attached with the carbon, then the positive charge which I can see on this carbon will have relatively lesser intensity. It looks like it is 1 unit of positive charge, but it will be lesser because some of the electron density would have been pushed by the electron donating group. Okay, so more and more electron donating groups will be present on the carbon carrying a positive charge. Stable will be your carbocation, because effectively your positive charge would have got nullified by the density which it has got through the electron donating group, and intensity of that plus charge would have decreased drastically and will make this carbocation much more stable. Instead of that, or contrary to this, if I have carbon with a positive charge and I attach electron withdrawing group to it, then what will happen? Anyways, the carbon had a positive charge. Now you have an electron withdrawing group present on it, which will pull further more electron density from the carbon. Then the strength of this positive charge will increase. More the positive charge or negative charge is, unstable your species is. So charges make the species unstable. So if the intensity of plus charge will increase, the carbocation stability will decrease. That's exactly is the reason for the stability of carbocation. That means if I have a plus I group on a carbocation, then its stability will increase because the intensity of plus charge will decrease. But if I have a minus I group, which is nothing else but electron withdrawing group, then the stability of carbocation will decrease. Why? Because it will pull the electron density from the carbon carrying positive charge, and the strength of positive charge will increase, which will make the carbocation unstable. This is very important to understand. Just understand one thing, more and more charge on any species, positive, it can be positive, it can be negative, any kind of charge, if it is more charge over there, then the species is unstable. So you have to try reducing the strength of the charge. You have to decrease the intensity of the charge. Whichever way it is possible, just decrease it. Decrease in the intensity will make the species more stable. Okay, so here let's look at the tertiary carbocation. So if I talk about tertiary carbocation, here is the here we are going to talk about the plus I effect, what we had discussed earlier, so that how plus I effect is useful. So if you talk about let's say this compound, this is not compound, sorry, this is the intermediate structure. So this carbocation, if I talk about, then what is the situation over here? You look at it. So we have a carbon with a positive charge, and it has 3 CH3s attached to it. Okay. So 3 CH3s attached means this carbon will give some density to the carbon which is carrying a positive charge. This CH3 will also give some density to the carbon carrying positive charge, and this CH3 will also give some electron density to the carbon carrying positive charge. 3 direct CH3s are attached. So that means these CH3s are acting as electron donating groups, and the carbon carrying positive charge is acting as an electron withdrawing group. So when the electron density will come closer to C plus, won't the plus charge of carbon will decrease, or the intensity of the plus charge of carbon will decrease? It will, right? So if it will decrease, that means it looks like it is 1 unit of positive charge, but it would be way lesser than that, and hence it will be better stable. Look at the secondary carbocation. Now in secondary carbocation, I am just doing a relative comparison. Okay, so here you have to think it that way. So here I have only 2 electron donating groups. Earlier we had 3 electron donating groups. So more electron density was accumulated around C plus, which was reducing the intensity of plus charge. Here relatively lesser electron density is accumulated around CH plus, and hence positive charge is definitely the intensity of positive charge is definitely decreased, but not as much as it was in the case of tertiary, and hence it is relatively lesser stable. Come to the primary one, only 1 electron donating group is present. Hence, definitely the density, electron density will be pushed towards CH2 plus, but it is not as much as secondary and tertiary, and hence the positive charge will be, the intensity of the positive charge will decrease, but not as much as secondary and tertiary, and hence it will be lesser stable. Come to the methyl group. It doesn't have anything apart from hydrogen as electron donating groups, or the major electron donating groups, and hence the positive charge is untouched. So basically it's a very strong positive charge, and it will make the species very unstable. Okay, so if you arrange it through the stability order, tertiary has the least positive charge and hence more stable, then secondary, then primary, and then methyl. This is the reason why your tertiary carbocation is more stable, then secondary, then primary, and then methyl. This is the reason for the stability order of the carbocations. Okay, so we can write it over here as stability order of carbocation is tertiary, secondary, primary, and CH3. I told you the reason. Lesser the positive charge, stable will be the species. Least positive charge is on tertiary, and hence it is the most stable one. Now let's use this concept and try to solve some questions. So here is my question. Okay, so I have 3 compounds over here, and I have to arrange them according to their stability. All the 3 are carbocations. Now we have to see which carbocation is more stable than the other. So you have to arrange them according to the stability order. What should be the first step? The first step is to figure out the degree of the carbocation. So the plus charge is on this carbon. In this case, the plus charge is on this carbon, and in this case, the plus charge is on the center carbon. I know it is not very clearly written, but this is how exactly it is. Now you try it out on your own and then tell me what should be the stability order. Or you try out these 3 questions on your own, and then we will talk about the stability. So now let's see. In case of A, what kind of carbocation it is? It is, if you resolve the structure, it is CH2 plus. So basically this is a primary carbocation. This is primary carbocation. Okay. Now come to the second one, that is B. This is This is attached to one carbon over here, this is attached to another carbon over here. So this is secondary carbocation. I hope you will be able to at least figure out what kind of carbon it is, whether it's secondary, primary or tertiary. In the third case, in C, the carbocation is tertiary carbocation. How it is tertiary? Because it is attached to one carbon here, and one carbon here. So to check the degree, you just have to see what are the direct attachments or how many direct attachments with carbons are there. So this is tertiary carbocation. Just now we have learned that tertiary carbocations are most stable. So C is gonna be most stable, then your B, and then your A. Okay, this is how we'll apply the plus I effect concept on the carbocation stability. Now let's understand the second one. In case of second, I have carbon with a positive charge with 3 Ds present and another carbon with 3 hydrogens present. I told you deuterium has a better electron donation capability than hydrogen. So D will donate it to the carbon, D will donate it to the carbon, and D will donate it to the carbon. So positive charge density will decrease on this carbon more when the D is present as compared to hydrogen. So if somebody asks me which species is better stable, CD3 plus is more stable than CH3 plus because the electron density around carbon carrying positive charge is more in case of CD3 as compared to CH3. Now come to the next question. Next question, again we have some carbocations over here. Okay, and we have to just figure out which one is most stable. Or we have to arrange it in the stability order. So look at the first carbocation. This is our primary carbocation. Okay, even the second one is I think there is a small mistake in this question. Let me correct it. So write it as CD3 over here. So this is also primary carbocation and this is also primary carbocation. So here degree of the carbocation is not changing. So what is changing which will change the stability of the molecule? Here all the carbons have hydrogens. Here in this case only one carbon has deuterium. So deuterium means more electron donation capability. So this CD3 will have more donation as compared to these CH3s. Okay, so this will have better stability as compared to this. So let's say this is first compound, this is second compound, and this is third compound. So obviously second one is more stable than first one. Why? Because there is a CD3 which has more donation of electron or which gives more electron density towards the carbon, and hence this carbocation which is on the second position will get better electron density as compared to the first one. Now, in the third case, all the carbons have deuterium instead of hydrogen. Hence, definitely better electron donation as compared to CH3s. And hence, the electron density around this carbon will be more and this will be more stable. So third compound is most stable because more electron density around the carbon carrying positive charge, hence decreasing the intensity of positive charge drastically. And hence, this is most stable. Then the stability is for second and then the stability is for first. Okay, I hope you would have understood it. If you have not, ask me in the doubts class.